So hello everybody, I'm Michael Sarahan. I'm going to be talking to you about compatibility. Um, Although this is kind of in the ABI track, I'm going to be a little bit more broad than that. So you guys know who I am. I'm a former recovering scientist. Did a lot of code for running electron microscopes and doing data analysis. I joined Continuum Analytics, which is now called Anaconda, to work on building conda packages for Windows, and branched out from there. Worked a lot on conda and conda build, and I currently work for RStudio on Package Manager. So that's all to say that I don't have any formal computer science training. I'm not an expert on any of this stuff. I just play one on TV, and you should all correct me in the chat if I'm wrong. Okay. This talk mentioned Ray Donnelly in the abstract. For those of you who know him, he passed away in April this year. So I am a Tenacious D fan, and this is not the greatest ABI talk in the world. This is just a tribute to Ray. How do people encounter incompatibility? There's a few different ways that users find it. One way is that they can't run stuff, or they can't link stuff when the functions are wrong, or just things don't line up. And this is really what happens when the package manager or the solver goes wrong. And it's typically not that the package manager has a bug in it, it's that the packages themselves don't have adequate metadata to make sure that things line up okay. ABI stuff can be a little bit more complicated. Kind of a good fundamental definition of ABI incompatibility is when you can't use a newer version of a shared library when it was linked against an older version. It can happen for a lot of different reasons, as far as rearranging arguments to functions, removing symbols, and a few other things. And it can happen for all kinds of interesting and bizarre reasons, beyond just like the package manager did the wrong thing. So I'll be talking a bit about those here. To discuss a tiny bit about about what this whole islands of compatibility analogy is, I'm going to call an island a self-consistent set of software that may have many parts. You can install part or all of an island. Islands can overlap. They don't have to. They do overlap when a component from one is interoperable with another. So for example, if a system library provides bzip2 and that bzip2 shared library works with a PyPI package, say, then those two islands overlap. And errors happen whenever you think you have overlap, whenever you think that the islands share land, but they don't. They don't actually share that land. They're incompatible in some way. So who cares? Data scientists care, package maintainers care, system integrators. We talked about that a lot in the keynote, where distros are people who take all the parts and put them together and try to make sure that they work. Whereas library maintainers are more like the people on the language ecosystems, where they're just kind of putting a library out there, and they're not telling people how to use it with all these other parts. They're not providing people with the other parts. Whereas I'd say an application maintainer is somebody who is providing somebody with an integrated set of things that work. But overall, it's somebody who sees error messages like these and thinks these three letters, for anybody who knows sign language or wants to look it up. Thanks, Misha. Who usually knows what's going on? It's the meta maintainers. So it's people who maintain channels or cross channels especially. It's usually not the people who are maintaining individual packages, definitely not the users. So there's three main ways that I've seen users get shot in the foot by this, and people call shooting yourself in the foot. At Anaconda, we used to call it foot cannons, things that were potentially major problems. So these are three ways that people can see problems. If you mix ecosystems, then these are kind of by definition places where people have followed different build practices. So they may have used different compilers, they may have used different flags, and all of these things are implicitly encoded in the standard practices for that island, but they often aren't encoded in the metadata. If you put things in the wrong places, this leads to problems with the loader, whatever OS it may be, your shared library loader, can lead to things going wrong. So if you guys follow this link up here, you can see these slides, you can follow this story. It was basically a problem where a third-party vendor of another bit of software put MKL DLLs in the System32 folder, which always comes first in Windows. And so no matter what, Anaconda could not load the correct library here. So kind of an interesting story. And the end of it is that we tried to do a hack to even override Windows's loader, which is horrifying, because we're kind of opening the door to pretty huge malicious abuse of the loader. But even when you do that, you break other people's things. One other way that things break is when you try to merge two different islands in the same process. And so one common use case that happens is either trying to run Python code from R, which people do with Reticulate, or R code in Python, which you do with RPy2. And either way, you are taking the main process being either R or Python, and then you're loading libraries from a totally different ecosystem. So this causes a problem because those library ecosystems are almost certainly not compatible, and you end up with whatever library gets loaded in first is the one that wins. And so this is kind of showing you how the loader works in Linux. Every OS is different. But things get loaded by name, and they don't get loaded by particular symbols necessarily. And like the example in the keynote where JavaScript allows multiple versions to be loaded in memory at once, that's totally not true about most lower level compiled dependencies. So you can really easily end up in a situation where the first library that loads is definitely not the library you need for something later. So in summary, these things have to line up, or else you're probably going to crash. The package manager has to have all necessary data to ensure that the ABI and the ABIs line up. Package manager info should not be confused or degraded by introducing more than one source. So these are different conda channels, it's different repos for Red Hat, it's different PPAs for the Debian or Ubuntu world. And again, the problem is not so much that the software is incompatible. The problem is that the metadata does not account for the incompatibility. And so the package manager can't do the right thing there. And finally, within a process, you should try as much as possible to load stuff from a single ecosystem, because that's really the only way that you can guarantee that things are actually compatible. There's a few different proven ways that different ecosystems do line things up. I work on RStudio's package manager. Its approach is to use system libraries, and as a result, the packages that it compiles, it has to compile for every single platform that we support. So we build binaries for something like 6 or 7 different Linux distributions. and we have to build out that matrix for every new package that comes out. You can avoid the system libraries and build practically everything yourself. This is the approach that that Conda takes, and thus, also Conda Forge. You can define platform tags. This is Python's many Linux proposal. They limit the tool chains you can use, and they also say that you can't leave kind of dangling external libraries to be fulfilled by something. You can't do any TBDs. And unfortunately, this is a big limitation of PyPI. They don't embed enough data to kind of encode what external library dependencies there might be. You can statically link and or vendor. I kind of consider statically linking a form of vendoring, just because you're including the foreign code in your own binary. This is the approach that Bazel takes. Is really like a hermetic build approach. And you can also tell people that, hey, just build from source. And this is Cran's approach to Linux, and it's decent for when people understand compilers and when the compiler source stuff actually works perfectly. But it takes a lot more time, and it is more open to confusion. So I'm a Conda-centric person. Please excuse my limited view here, but I think that there have been some great successes recently that have dramatically improved the quality of Conda's ecosystem. The first has been Conda Forge as an organization, which took a lot of separate channels and tied them all together, and thus unified all of their tool chains and their core libraries. So Conda Forge as a social construct has had enormous technical benefit. If you guys have never seen ABI Laboratory, I highly recommend you check out this link. This guy just runs tests and tells you about when symbols have been removed and whether or not a future version of a library is likely to work. And so when we found this site at Anaconda, we were able to start encoding information in our metadata about how far forward we expected libraries to be compatible. And so we could start writing expressions that said, this package is built with OpenSSL 1.1.1.a, and it should be compatible with any future 1.1.1 release. So that kind of metadata is really, really helpful for giving your packages durability. Conda Forge's bot has been huge for automating things and for making many of these system-wide changes feasible, right? When you change a system dependency like the compiler and you need to recursively rebuild everything, the bot is really the only viable way to do that. I'd say the many Linux standards have been enormous for PyPI, for anybody doing pip stuff, because it was really the Wild West before that, right? There was no good way to install pip packages on Linux. And finally, pip introducing a proper dependency solver. If you're not in the Python world, you may not have heard much about this, but pip used to resolve just one package at a time, and it would very commonly break environments by breaking dependencies that you had satisfied in the past. So I'm really proud of the work that a lot of people have done, and I'm certainly hopeful about the future. What I think the future holds is that we really need to move towards more and more metadata. And so package managers can't interoperate because the metadata that they share is woefully inadequate to establish compatibility. What I would like to see, what I hope to work on someday is something like an LDD tool that really is resolving symbols, not just file names. But this is a kind of a very, very different scale. So just As an example, the dependencies that libgdal, which is admittedly a very complicated library, it's 45,000 different symbols to think about resolving. And so maybe it's like a validation step after a solve, something like that. But it's probably not, you can't just straight up solve for symbols. Yeah, and and with that, I am done here, and I'm open to questions from you guys.
Hi, Michael.
Hi.
Um, yeah, surprising enough, you can't. Let me check the channel for any questions. Um,
Yeah, so
I
there's a good question about can you instead call the other ecosystem via a subprocess and use shared memory with something like Arrow for sharing data? Are there common libraries for doing this? Yes, that is a great idea. The way that that RPi2 and Reticulate work right now is that they copy the memory, but I think you'll probably see, I think Arrow is a great way to do that, and you'll probably see Reticulate or these other libraries start to move forward with straight memory sharing and some RPC stuff.
So you did talk about sharing more metadata. What ways can uh, what ways can we bubble up more metadata to things that are consuming these libraries?
Um, so I think it's a matter of like identifying anything that affects compatibility. And so when I talk about symbols, this is like the most granular thing you can possibly think of. It's like all the possibly mangled definitions of the functions and things like that that get exported. And it, like I said, it's probably not something you could feed into a solver. It's just too crazy, but it is something that you could validate when you create an environment to say, do I have all the stuff I need to run this? And so, yeah, you can think of exporting all of the symbols that a library provides. And similarly, you can think of exporting all of the symbols that a library imports, right? What things provide and what things actually consume. Um, Before you go to that extreme, um, you can do things. So one of the things we did in Conda was to encode like the versions of packages that we built with and how that affects the runtime dependencies. So we introduced kind of a it's called pin compatible is the concept in a Conda recipe, but it's to say that you impose runtime constraints in your recipe that are based on your build time, whatever you have present at build time. And those are not always just dependencies on the package you built with. They may be dependencies on, say, glibc of a particular version. So the compiler package in Conda will impose a particular glibc version. And even though Conda doesn't provide glibc, um, it tracks it via a meta package, and that's one of the things I mentioned in my talk. I'm not sure if I actually talked about it, but Conda can use these external meta packages to track state, and this is kind of the infancy of talking to external package managers and understanding when you can like when you can get away with what's there and when you need to provide your own.
There's a question, could you go the other way and use the symbols to reduce the solve space?
I think you probably could. I'm not sure. So like the symbols are enormous and relative to the package namespace, and it's just kind of an implementation detail, but I think it would be more efficient to reduce the space with the solver and the package names first, and then go into the resolution of the symbols. But sure, I think all approaches are worth exploring.